Okay, so in this video, I'm just gonna try to explain the dot product idea and how that relates to projections and the problems you have to do in this section. So this is in 13.4 dot products. So let's just really quickly just write out the dot product of two vectors is when you take the first component of each of the vectors, you multiply them, you add the second components of each of the vectors and multiply them, and you get the dot product. You also have this other formula for a dot product where you take the cosine of the angle in between them, and that's equal to the dot product of the two vectors divided by the magnitude of those two vectors multiplied together. So this gives you the idea that the dot product has something to do with like the effect of a vector on another vector and it has some relation with the angle in between two vectors. So that's kind of how it relates them and talks about the effect. We have some sort of scaling bit because that's the actual effect that it changes a vector. And there's also something to do with the angle in between them because that angle in between them affects how much it can scale another vector by. So together that gives you some idea of like what goes into that number that comes out of the dot product. And this helps us to think about projections, which is the new concept in this section. So projections, kind of this idea of, let's think of a really simple example of this. So if you have the x and y plane, and you have a vector in it, let's say this is the vector going this way, it goes up to the point 4, 5. So then this vector would be 4, 5. If I'm thinking about moving along this vector, if I only care about how much I move horizontally, so I'm not going to look at how much I'm moving vertically, I only care about on the x-axis, in the x-axis direction, I'm moving 4 units. So that would be 4, 0. And then I'm going to forget about the x-axis. I'm only going to look at the y-axis. And I want to look at how much am I moving on the y-axis. And that would be 0, 5. One thing that I want you to notice here is these are two components of my final vector. If I add up my two components, so this is how much I'm moving in the y direction, and this is how much I'm moving in the x direction, when I add them up, I get my actual vector that I had in the end, the 4, 5. So this idea of looking at just unidirectional movement, so even though my actual movement is this diagonal bit, I'm only looking at how much I'm moving in the x direction, how much am I moving in the y direction. When I look at how much I'm moving in the x direction, that's a projection of this vector on x. And then when I'm only looking at what I'm moving in the y direction, that's a projection on the y-axis. So where the projection formula becomes more useful, because this projection we could figure out without having to use any formula. We just literally looked at the components here, made a right triangle out of it. Is if you think about, we're not always looking, we don't always care about just horizontal and vertical motion. Sometimes we care about how much is this motion and this motion. So I'm kind of tilting the x and y axis now to be these two axes. So I could still have my same vector, but now I don't care about this bit. So let me call this v. So I don't care about my x direction motion, right? This would be my x direction motion. I don't care about that. What I actually care about is how much am I moving on this v vector. So how much am I moving along the v vector when I go on this diagonal bit. So I'm still projecting, I'm still doing the same thing I did here, like I'm kind of creating a right triangle over here. I care about how much I'm moving in the v direction, and then how much am I moving in this other direction that's perpendicular to v. So the formula to get that, so to get this equation, so if you just look at it geometrically, it's moving in the same direction as v, which means I need to get a unit vector of v. And then I'm also moving I need to figure out how much does this vector actually affect the v vector to scale it down, because it's not this whole big v vector, right? The way I've drawn this diagram, v goes from here all the way to here. But my projection, looking at my diagram, ends around here. So it's not going to go all the way. So I need to scale it down a little bit. So I need to come up with what that scaling factor is. So the formula for the projection, which takes into account both the scaling and the angle to make sure both of those are actually giving us this diagram. So the way we write it, first of all, so let's call this vector u. You take the vector you're projecting on, so you're projecting onto v, you put that on the bottom. You take the vector you're actually projecting. So this is the one you actually care about. This is the one you're moving, your actual movement is on. So you put that on the top. And so that equals the dot product of these two vectors. So dot products affect these things. The dot product is the effect that one vector has on another when you're looking at these combinations of things. Divided by, so this is going to look like this cosine theta formula because we are kind of looking at the angle between them. Except here, instead of multiplying two magnitudes, we're only going to take this vector magnitude and square it. This whole thing tells us how much to scale the v vector by. So this thing is how much smaller this bit of the vector is than this whole v vector. And since we're scaling the v vector, we multiply it to the v vector in the end. So this formula is how you get projections. Hopefully now you have some intuition around what that projection actually means and how this formula comes about. Because I haven't done a full proof of this and I'm not going into exactly what each of these components mean, but just sort of generally this is a dot product that gives you the effect of how much to scale a vector by. So you come up with a scalar and then you scale the vector that you need. So that's kind of how the dot product works. I'll go through the example. So this is the example that's in your textbook and that was on your notes. I'll just go through it again so you can hear it one more time. So this tells you have a vector u, which is 3, -5, and you're projecting it onto the vector v, which is 6, 2. And it tells you write the vector u as the sum of two orthogonal vectors, one of which is the projection of u onto v. So first we need to figure out what the projection of u onto v is. So if I think about a diagram of that, I have u that's 3, -5, so that's somewhere down here. And v is 6, 2, which is somewhere up there. And I want to know, on this v vector, how much is u actually affecting it? How much if I was walking along u, how much would I be moving in the v direction? So that's kind of, this highlighted bit is the vector I'm trying to find. Right, so that's kind of making a right triangle with u. So I figure out using the projection formula, so I'm going to call this w1. So my w1 vector is a projection of u onto v, where I dot product the two vectors, divide by the magnitude of v squared, and then multiply the whole thing to v. So the dot product here is 3 times 6 plus -5 times 2 divided by the square root of 6 squared is 36, 2 squared is 4, the whole thing squared. All of this scales my v vector 6, 2. So this is 18 minus 10, which is 8. The square root and the square go away. This is 40, so I get 8 over 40, which is the same as 1/5, times 6, 2, which is 6/5, 2/5. So that's telling me that this w1 vector, this is 6/5, 2/5. It's 1/5 the size of this whole v vector. Now I want to come up with, what is this other vector that's added onto it? So notice that when you do projections, what I showed you on the last slide was you can add them up to come up with the final vector you need. So here I have this other vector that's added on to w1. And when I add w1 and w2, I should get my u vector, right? If I look at this geometrically too, I have one vector at the edge of the other vector, and its endpoint connected to the origin should give me the addition of those two vectors. So I take 6/5, 2/5, and I add it to whatever my w2 vector is, and I should get back 3, -5. So if I think about how this works. I need to get some vector that's 3 minus 6/5 to comma -5 minus 2/5. And so that would end up being 9/5 comma -27/5. And this would end up being my W2 vector. This is my W1 vector. These two vectors together, if we add them up, gives us the U vector. So hopefully this gave you a little bit of the intuition behind projections and dot products and how they kind of relate to each other, a problem on how to solve one of these questions, and hopefully you'll be able to go through some of the homework problems and practice this more.